In this video, I'm going to briefly touch on the main concepts from yesterday's lesson. So we started off with concepts that were taught to you in Algebra 1, 2, and the first part was very procedural. It's if I give you the equation, how do you come up with the inverse? And so what we do is we start by switching the x and y. That is our very first step. After we switch the x and y, we want to isolate the y. Opposite of subtracting is adding. Notice that I'm showing all of my steps, and I expect you to do the same on the quiz. Now, how do I remove the negative 1/2 so that y is by itself? I'm going to multiply by the reciprocal, which is negative 2 over 1. Negative 2 over 2 reduces to 1, negative 1 over 1. There we go. It all reduces to 1, and I'm left with simply y on the right-hand side. When I distribute, I get negative 2x. If you want to put a 1 on the bottom, it's not wrong. And negative 6. If you want to put a 1 on the bottom, it's not wrong. Now, how do I identify this as being the inverse? I'm going to put a little negative 1 here. This is the inverse of this function. Okay, let's do the next one. Same thing. I'm going to switch the x and y. After I switch the x and y, I want to isolate the y. So I'm going to start by subtracting 1/5. You'll be doing the same. X subtract 1/5 equals 3/4 y. Now I'm going to multiply by the reciprocal of 4/3 to both sides, and I'm going to slow this down just a little bit. These all reduce down to 1. When I distribute, 4/3 times x is 4/3 x. This is the confusing part for students. This 4 gets multiplied by the top, or the numerator, which is 1. 4 times 1 is 4. 3 times 5 is 15. It can't be reduced. And this is the this is the inverse of this original function. Now, before we touch on your understanding of a function and its inverse relationship, let's look at this random table. If I asked you, I said, this is function f, and I want you to represent the inverse of f. This is function f, and I want you to represent the inverse of f in a table format. What would we do? Within your groups, you may or may not know people. Turn to the people in your group. How could I represent the inverse of this function to the right? Go ahead. You have 5 seconds. Go. What would we do? And if somebody says you switch, and they weren't here yesterday, and they're like, what do you mean you switch? You would say, okay, we're going to take the input values, the x values. We're going to take the input values, and instead of rewriting them in the same position, the input, we're going to rewrite the input values in the outputs of the inverse. So negative 2, negative 1, 0, and 1. And I'm going to take the output values of the original function, and I'm going to place those in the input values of the inverse. So if somebody said to us, hey, can you explain the inputs, how the inputs and the outputs relate for the function and its inverse? You would say the inputs of the original function become the outputs of the inverse. The outputs of the original function become the inputs of the inverse. You cannot say they switch. You cannot say they flip. You need to expand. Does anybody need me to say that once again? Okay, we're going to go on to the next problem. Now, all that is related to what you learned in Algebra 1, 2. This is the Algebra 3, 4 concepts. Algebra 3, 4 concepts say, okay, you're given two functions, and you either want to show that they are inverses of one another, or maybe they're not inverses of one another. But let's figure out how to do this. So, how we do this using algebra is we use a concept called composition of functions. So I'm going to call this y. I'm going to write down the first function, and wherever I see an x, I'm going to leave a fairly large space and put either brackets or parentheses in that area. Now, in this open space, I'm going to come to the second equation, and I'm going to write it down. So 3x minus 3/5. Now we're going to go ahead and we're going to simplify. So really there's like a 1 underneath, if that confuses you. 1 times 3 is 3. 3 times 1 is 3. Bring down the x. 1 times negative 3 is negative 3. 3 times 5 is 15. And when I simplify, I end up with 1x. Well, this reduces to negative 1/5. Notice I'm showing all of my steps. These are additive inverses. Additive inverses cancel out. I showed all of my steps, and I ended up with y equals x. If I have y equals x, not y equals negative x, not y equals 1x plus 3, simply y equals x or y equals 1x, then I move forward to the next step. I'm on track right now to show that these are inverses of one another. Now I start with the second function. Again, wherever I see an x, I leave a large open space. with parentheses around it. I come back to the first equation, I write it down, and I'm going to move forward here. 3 times 1 is 3 with a 3 in the bottom. 3 times 1 is 3 with a 5 on the bottom. 3 over 3 is equal to 1. And these are additive inverses. That means they're directly opposite. They cancel out, and I end up with g of x equals 1x. So did I just prove that they are functions, yes or no? Yeah. They are functions of one another because I got y equals 1x, or y equals x both times. Okay, so yes, they are functions of one another. Let's try the next one. Okay, I'm going to start here. Y equals negative 1 half, leave a space. Then in this area, I write down 2x minus 6. And here we go. Negative 1 times 2 is negative 2. 2 times 1 is 2. Negative 1 times 6 is positive 6 over 2. Okay, keep going. Y equals negative 1x plus 3 minus 3. Additive inverses, they cancel out. Okay, turn to your group. Do I keep going or do I stop? Turn to your group and tell them, do I keep going or stop? What is your reasoning? You stop. Why do I stop? Did I get y equals 1x or y equals x? I didn't get that because there's a negative sign. So no, they are not inverses of one another. Okay? All right, let's move on to the very last piece of this. The very last piece of this is, what if I give you a random line and I give you an actual graph with this random line and I ask you to accurately graph the inverse of this function? I can think of 3 ways to accurately do that. So I want you to turn to people in your group. I only had 2 groups in first period. I know it's first period, people are tired. I only had 2 groups talk, and those 2 groups came up with vastly different approaches that would both work. One, they could probably be done in 5 seconds. One would probably take a minute, but vastly different approaches. How would you accurately graph, if I put this right in front of you right now, how would you graph on this Cartesian plane the graph of the inverse of the red function? Ready? As a group, you have 15 seconds. What would be your approach? Go. Start talking. What would you do? It's okay to say, I'm not really sure. So I'm going to start with the longest way. Here's the longest way. And I had a student do this. Can anybody tell me, so we have a linear line, it's straight. Can anybody tell me what is the y-intercept of the function that's in red? 6. Okay, I'm going to write that down. Y, and that's a positive 6. Now, let's figure out what is the slope. So let me take this line. Okay, there's a good intersection point. There's a good intersection point right. It's 3 right there, right? So I have to go up 1 over 3. Does everybody see that? From left to right, up 1 over 3. So here's one way that we could do it. Okay, up 1 over 3. Here's the original function. If I need to find the inverse of it so I could graph it, I'm going to switch the x and y. And then I want to isolate the y. So I'm subtracting 6 to the opposite side. I'm multiplying by the reciprocal. The 1s and the 3s are going to simplify to 1. And then I go 3 times x is 3x. 3 times negative 6 is negative 18. There is the inverse. I come back to this graph. Give me 1 second. This is the equation of the inverse when I did it procedurally. And then I came back here and I actually graphed that. And we can see it. We're like, well, do I think that that represents the inverse? I'm not really sure. If you graph the line y equals x, we learned yesterday, and you should have learned that in Algebra 1 too, that both the inverse and its relation, so the original function and the inverse function should always reflect across the line y equals x. Now, there's an easier way to do this. So I wouldn't have chosen this route. Here's what I would have done. I would have gone to this function, and I would have picked out good intersection points, like 0, 6. And then all I would do is I would take the x and make it the y of the inverse, and take the y and make it the x. So 0, 6 becomes 6, 0. And then here's another one. I'm going to find 6, 8. So does everybody see how this is a good intersection point right here? 6, 8. Well, 6, 8 becomes what when we flip it? It becomes 8, 6. And the same thing. I would find 12, 10. And 12, 10 is right here. It's a good intersection point. And when I flip it, becomes 10, 12. So those are my points. And then I would just simply take my ID, I'd put a line through them, and I graphed it. So I would personally not take time, if it didn't say I had to use algebra, to do all of this work. I would simply go ahead and find good intersection points on the original function, flip the X and Y, plot those points, and then connect it. Since there was a lull in my instruction taking that office call, please make sure everybody in your group understands that before we proceed forward. Go ahead.